Welcome back, Design Junkies, to Mechanical Engineering Made Simple. If the podcast brings you value, help support the show with a like, a follow, or leave a comment below. If you are sitting inside a building right now or maybe driving your car, you are currently inside a structure that is actively trying to destroy itself.
It really is.
Yeah, gravity is constantly pulling it down, daily temperature swings are warping it, and, well, invisible microscopic cracks are likely forming deep inside the materials at this very second.
Which sounds terrifying when you put it like that.
Right. But you aren't worried about the roof collapsing. Why? Because decades ago, engineers figured out the math to predict the chaos.
Exactly. It is entirely about taming the physical world through numbers. And if you want to know how they do it, you really have to look at the foundational texts, the rule book.
And the one we are diving into for this deep dive is an absolute legend in structural engineering. We're looking at Roark's Formulas for Stress and Strain, 7th edition, by Warren C. Young and Richard G. Bodinas.
It's the Bible for this stuff. If you are designing anything that has to hold up under pressure, from a basic wooden shelf in your garage to a commercial airliner flying at 30,000 feet, the core rules are locked inside this book.
But let's be honest with the listener here. If you just open this book cold, it is terrifying.
Oh, absolutely.
You are hit with a literal wall of massive tables, endless Greek variables, and, equations that span entire pages.
It can absolutely look like an alien language.
Yeah.
It is incredibly dense because it's trying to account for, well, almost every physical scenario a material might experience.
Which is exactly why we are doing this deep dive. We are going to act as your translator today.
Right.
We are bypassing the overwhelming data tables to extract the vital foundational concepts hiding underneath. The goal is to understand why the physical materials around you behave the way they do when you, bend them, squeeze them, or leave them out in the rain.
Yeah, and how engineers use these precise mathematical rules to keep us all safe. But to really grasp that, we can't start with the massive equations.
No, we really can't.
We actually have to flip all the way to the back of the book, to the glossary in Appendix B. Because before you can even begin to calculate a structural failure, you have to speak the vocabulary engineers use to define the limits of a material.
That makes perfect sense. If you don't know the terminology, the math is just abstract noise.
Exactly.
So let's unpack this language of limits. The first major distinction I noticed in the glossary is between two terms, allowable stress and damaging stress.
A critical distinction.
Yeah, and for you listening, the best way I can visualize this is thinking about a highway speed limit. Allowable stress is that speed limit.
Okay, I like that.
It is a calculated boundary designed for safety. They set the speed limit at 65 so you can drive safely whether it is raining, whether there's heavy traffic, or, whether your tires are a little bald. You have a massive margin of security.
Right.
Damaging stress, on the other hand, is the literal mechanical limit of your car. It is the point where you press the accelerator to the floor, hold it there, and your engine literally explodes.
That is a highly accurate way to look at it, honestly.
Mm-hmm.
The gap between driving 65 miles per hour and blowing up your engine is the entire focus of an engineer's job.
That whole gap.
Yeah. In their vocabulary, allowable stress, sometimes called working stress, is the absolute maximum stress they calculate for the expected everyday conditions of service.
So it has to be way lower than the damaging point.
It must always be kept significantly lower than the damaging stress, which is the exact point where a physical part permanently breaks or becomes completely unfit to do its job. But the interesting part is exploring why that gap is so large.
Right, because it isn't just an arbitrary cushion, is it?
No, not at all. It accounts for three very specific, unavoidable uncertainties.
Let me see if I can guess these, because it feels like building things in the real world is inherently messy.
It really is.
First uncertainty, I would guess unpredictable weather or crazy loads. Like, you build a bridge for normal cars, but what if a parade of cement trucks decides to cross it during a hurricane?
Spot on. That is the uncertainty of service conditions. You can never perfectly predict the extreme fringe events a structure might face. What is your guess for the second uncertainty?
I would say the physical materials themselves.
Okay, yeah.
Like, if I go to the hardware store and buy 10 steel bolts, they might look identical, but I bet on a microscopic level they aren't. There have to be tiny flaws from the manufacturing process.
You are hitting on a major headache for structural designers. Non-uniformity in materials. You might order a massive batch of high-strength steel, but the internal lattice of that metal will have natural, microscopic variations.
So no two pieces of steel are truly identical twins?
Exactly. Okay, so we have unpredictable loads and flawed materials. Is the third uncertainty human error? Like a guy at a drafting table just forgets to carry a 1 in his calculations. It's actually a bit deeper than human error. The third uncertainty is the natural inaccuracy of the stress analysis itself.
Wait, the math itself is inaccurate.
Well, the mathematical models we use, even the brilliant complex ones in Roark's, are ultimately just approximations of reality. They are forced to make assumptions.
Oh, I see.
So the less certain an engineer is about the service conditions, the material reliability, or the exactness of their own mathematical models, the wider that gap between allowable stress and damaging stress needs to be.
Wow. So the math is brilliant, but it is humble. It knows it cannot perfectly mirror the chaos of the universe.
That's a great way to put it.
Speaking of limits, there's another definition here that sounds very specific. The apparent elastic limit. The book defines it as the exact point where the rate of change of strain with respect to stress is 50% greater than it is at zero stress.
Yeah, that's a mouthful.
Right. Okay, I read that and my brain immediately stalled. Why 50%? What is the actual physical mechanism happening there?
Let's ground it in reality.
Yeah.
Imagine you are holding a steel rod and you start pulling on both ends. At first, the steel acts like a perfectly behaved spring.
Okay.
You pull with 100 pounds of force, it stretches 1 millimeter. You pull with 200 pounds, it stretches 2 millimeters. It is a purely proportional relationship.
So it's fighting back equally.
Exactly.
Yeah.
But eventually, the internal bonds of the steel start to give way and it begins stretching much easier.
So it's like a thick rubber band that suddenly stops fighting back as hard and just starts stretching out uncontrollably.
Yes. The apparent elastic limit gives an engineer a very definitive, determinable point on a graph to look at. It is the moment the material is yielding 50% faster per unit of force than it did when you first started pulling it.
Oh, got it.
It's incredibly useful because it lets you compare different materials side by side to see which one will hold its structural integrity the longest before it starts to rapidly give up.
That makes a ton of sense. It is a benchmark for material stubbornness.
I like that. Material stubbornness.
There's another term here, bulk modulus of elasticity. The glossary describes it as the ratio of a triaxial stress to the relative change it produces in volume. Triaxial stress sounds like, I don't know, a torture device where you're being squeezed from all sides at once.
Well, that is precisely what it is. Think of extreme hydrostatic pressure.
Like underwater.
Yeah, if you take a solid block of rubber and sink it deep into the Marianas Trench, the ocean water is pushing inward with massive force from the top, bottom, left, right, front, and back simultaneously. That equal squeezing from all directions is triaxial stress.
So the bulk modulus of elasticity is just measuring how much that deep ocean pressure physically shrinks the rubber block.
Yes, it is a mathematical measure of a material's fundamental compressibility. How much can you shrink its physical volume without changing its overall shape?
Okay, so we have the vocabulary down. We understand speed limits, breaking points, and how materials respond to being pulled or squeezed from all sides. But structures aren't just solid blocks sitting in the ocean.
No, they're not.
They're made of individual parts. That leads us to beams. Straight beams, curved beams, I-beams. They are the skeleton of our world.
Beams are the fundamental building blocks of almost any structure you interact with. If you want to master structural engineering, you really have to understand exactly how beams handle weight.
And here's where I need to push back on the book, or at least admit where I got confused.
Okay, let's hear it.
If I take a straight wooden beam and I put a massive anvil right in the center of it, I know it bends downward in the middle. I can visualize that perfectly.
Sure.
But when we look at the complex formulas in works, how does the math actually distinguish between the structural forces happening on the left side of the anvil versus the right side? To my brain, it's all just one big pile of downward gravity.
That is a fantastic question. And it introduces a concept called the bending moment. You are right that gravity pulls straight down, but the beam itself is experiencing rotational forces.
Rotational.
Yeah, and the math has to pick a perspective to make sense of it all. For convenience, engineers usually set an origin point at the far left end of the beam. The bending moment at any given slice of that beam is the sum of all the rotational forces, the moments acting on it, to either the left or the right of that slice.
So it's essentially picking a fixed camera angle to view the physics.
Yes, and standard convention dictates how we describe the bend. A positive bending moment means the beam is deforming concave upward. Picture a physical smile.
Okay.
The outer ends are pointing up and the middle is sagging down.
Mhm.
A negative bending moment means the beam deforms concave downward, which looks exactly like a frown.
A smile and a frown. That is a brilliant way to visualize it. Positive is a smile, negative is a frown. But the forces acting on the beam are only half the story. The physical shape of the beam itself matters just as much, right? I was looking at Appendix A, which just lists the properties of different cross-sectional shapes. And the formulas here seem to dictate the ultimate strength of the material.
Cross-sectional shape is arguably the most important decision an engineer makes. Let's look at a very standard shape from the book, a solid rectangle. Think of a standard wooden 2x4.
Right.
We can translate the math from Appendix A directly into a physical object. For a solid rectangle, the total area equals B times D. That is simply the base dimension multiplied by the depth dimension.
Simple enough. Area is just width times height.
Then we have the centroidal axis. This is the exact center of balance of the shape. For a vertical load, the centroidal axis, which the math calls y sub c, equals d divided by 2. It's just the halfway point of the depth.
Okay, still following.
But here is where the math dictates the physical design of every house ever built. The moment of inertia.
The moment of inertia. This is the property that dictates how fiercely the beam will resist bending when you step on it.
Correct. For a solid rectangle, the moment of inertia denoted as I sub x equals 1/12 multiplied by b multiplied by d cubed.
Wait, let me make sure I'm wrapping my head around this. So the formula is 1/12 times the base times the depth cubed. The depth is taken to the third power.
The depth is cubed, yes. And that tiny exponent explains everything about structural framing. Because the depth is cubed, increasing the vertical height of a beam has an exponentially greater effect on its stiffness than making it wider.
Oh.
The formula specifically points out that I sub x is much greater than I sub I if d is greater than b.
Oh, wow. Okay, think about that wooden 2x4 again. If you lay it flat on the ground like a plank, the vertical depth is only 2 inches. 2 cubed is 8.
Right.
But if you stand that exact same piece of wood up on its narrow edge, the vertical depth is now 4 inches. 4 cubed is 64.
You see it now. Just by turning that piece of wood 90 degrees, you increase its mathematical resistance to bending by a factor of 8. You didn't add a single ounce of material, you just changed the orientation of the depth.
That completely explains why floor joists in a basement are all standing vertically on their skinny edges instead of lying flat. The math demands it.
It absolutely demands it.
But the beam's shape and orientation still aren't enough. A beam floating in a vacuum doesn't do anything. It has to connect to walls or pillars.
Right, and those connections are called boundary conditions.
Yeah.
And they physically pin the math down to reality. The edges dictate the behavior of the entire span.
How so?
Well, for example, if you have a beam with a fixed end, meaning it is bolted fiercely into a thick concrete wall and cannot pivot even a fraction of a degree, the boundary conditions state that there is 0 displacement and 0 slope at that end. The mathematical formula has to lock those specific variables at 0.
But if you have a freely supported edge like a wooden plank just resting loosely on a brick ledge, it is allowed to pivot.
Exactly. For a freely supported edge, the boundary condition is a 0-stress state at that very edge, because the beam is free to rotate without the wall fighting back.
It's like pinning down the corners of a map before you start drawing the roads. The edges define the limits of everything in between.
That's a great analogy.
Okay, so the math perfectly explains what happens when I load a beam with an anvil right now. We map the forces, the shapes, the smiles, and the frowns. But what if I leave that anvil there for 10 years? Or what if I leave the beam out in the freezing rain? We have to account for the invisible enemies that act on materials silently over time.
We do, and this is where engineering gets truly complex. Some of the most catastrophic structural failures in history didn't happen because someone put too much weight on a beam.
They didn't.
No, they happened because of environmental forces that were completely invisible until the very last second. Let's start with a terrifying one. Brittle fracture.
Brittle fracture. That sounds like dropping a pane of glass on a tile floor.
That is the perfect mental image. Brittle fracture is a tensile failure, a pulling failure with almost 0 plastic deformation. There is no warning. Material doesn't stretch, it doesn't groan, it doesn't sag, it just snaps instantly.
Wow.
Now, as you said, we expect this in inherently brittle materials, glass, ceramics, cast iron. If you hit a ceramic coffee mug with a hammer, it shatters. It doesn't dent.
Right. But we build bridges out of structural steel because steel is ductile. It's
Oh,
supposed to
yeah.
stretch and bend before it breaks to give us a warning.
It is supposed to, yes.
Yeah.
But what is remarkable and incredibly dangerous is that normally ductile materials like structural steel can suddenly suffer a brittle fracture under three specific conditions.
What are they?
First, if it contains microscopic flaws or notches exceeding a certain limit. Second, if it is placed in a severely low-temperature environment. And third, if it experiences incredibly high strain rates.
When you say high strain rates, you mean the physical force is applied so unbelievably fast, like an explosion or a high-speed vehicle impact, that the steel simply doesn't have the time to stretch.
Exactly. The internal atomic lattice of the metal physically cannot rearrange itself fast enough to stretch, so it just tears apart like glass. And if you take a tiny scratch in a steel beam and introduce freezing temperatures, that scratch becomes a ticking time bomb. The cold locks up the atoms, preventing them from yielding.
That is genuinely terrifying. It completely changes how you view a winter storm. What about rust? How does something as mundane as corrosion play into these massive equations?
Roark details a devastating phenomenon called corrosion fatigue. Fatigue is the weakening of a material caused by repeatedly applying and removing a load, like cars constantly driving over a bridge, bouncing it up and down.
Okay.
But if that repeated bouncing is happening in a corrosive environment, say, a steel bridge suspended over a bay, constantly blasted with saltwater spray, the chemical corrosion actively eats into the microscopic fatigue cracks as they open up.
So the rust is essentially wedging itself into the microscopic cuts every time the bridge bounces. It's not just addition, it is multiplication. The rust and the bouncing make each other worse.
They are a devastating team. The math proves that this combination drastically lowers the material's lifespan far beyond what normal fatigue or normal rust would do alone.
And there is another invisible enemy the book mentions called creep. I've heard the term, but I always pictured it as something organic, like ivy growing up a wall. How does engineering define creep?
Creep is the continuous, agonizingly slow increase in deformation under a constant, unchanging stress. You place a heavy load on a steel member, and it holds it perfectly fine today. The apparent elastic limit is secure.
Right.
But over months or years or decades, it just slowly continues to stretch. The term creep is usually applied to metals under tension at elevated temperatures. The heat fundamentally changes the metal, making it want to slowly flow over time, almost like a hyperviscous liquid.
Wait, really? So the
Yeah.
metal actually stretches further over time, even if you don't add a single ounce of new weight, just because it's hot?
Just because it's hot and the load is constant. Now, if this same slow yielding happens under compressive stress where the material is being squashed down like a pillar rather than pulled like a cable, it is called plastic flow. And if this slow yielding happens at normal, everyday atmospheric room temperatures, it is simply called elastic drift.
Creep, plastic flow, elastic drift, they're all just different flavors of a material slowly giving up its structural integrity over time. But how on earth do you put a number on that? How does an engineer calculate a strain they can't even see?
The formulas in Roark's bridge the gap between thermodynamics and physical stress. For example, to calculate volumetric strain, how much a material physically changes size under pressure and temperature, the formula says the change in volume divided by the original volume equals the difference of 1 and 2 times nu, all multiplied by epsilon.
Okay, stop right there. I see nu and epsilon and my eyes just glaze over. What do those Greek letters actually mean in the physical world?
Fair enough. Let's make it physical. Epsilon represents the physical strain, the actual amount the material is squished down from the top. Nu is Poisson's ratio, which measures how much a material bulges out at the sides when you squish it.
Oh, like stepping on a marshmallow?
Mm.
The squish downward is epsilon and the marshmallow bulging out sideways over your shoe is nu?
That is a flawless analogy.
Okay.
Yes. So the formula combines the downward swish, the sideways bulge, and the temperature to tell you exactly how the total volume of that marshmallow changed.
Okay, I can see that.
We can also calculate the invisible energy stored inside a material. The formula for strain energy, which they denote as U, equals 1/2 P multiplied by delta.
Okay, let's translate that one. U is the pent-up strain energy. P is the physical load, the weight sitting on it. And delta is the deflection, how much it physically bends. So you multiply the weight by the bend, cut it in half, and that gives you the invisible coiled-up energy trapped inside the metal just waiting to snap back.
Exactly. You are taking invisible forces, heat, time, stored energy, and forcing them into measurable, manageable numbers.
This is incredible, but it brings up a massive question for me.
Okay, what is it?
We have cross-sectional shapes, we have marshmallows bulging, we have rust multiplication, we have pent-up energy. We are looking at equations in Roarks that have 15 different variables. How does an engineer look at a massive equation and know it isn't just mathematical nonsense? How do you prove the math is grounded in physical reality?
That is the ultimate safeguard, and it is covered in the Principles and Analytical Methods section. It is a concept called dimensional analysis.
Conventional analysis.
Right. This is the idea that the math isn't just abstract numbers floating in a void. Every single number represents a physical dimension, length, weight, time. An equation is only valid if it is dimensionally homogeneous.
Dimensionally homogeneous. So that means the units of measurement have to balance out perfectly on both sides of the equal sign, like a scale.
It is the ultimate reality check. If you are calculating the physical deflection of a beam, and the answer you are looking for is a distance measured purely in inches, then all the complex, messy math on the other side of the equal sign must resolve to inches.
Okay, let's do this as an audio puzzle for you listening to really nail this down. Say my target answer is in inches. The math on the other side is a massive fraction. On the top layer, the numerator, I have pounds per inch multiplied by inches to the fourth power. On the bottom layer, the denominator, I have pounds per square inch multiplied by inches to the fourth power.
So if we do the algebra on those physical units, what cancels out?
It is like a magic trick. On the top layer, you have pounds per inch multiplied by inches to the fourth. One of those inches cancels, leaving you with pounds multiplied by inches cubed.
Yep.
On the bottom layer, you have pounds per square inch, so divided by inches squared, multiplied by inches to the fourth. Two of those inches cancel, leaving you with pounds multiplied by inches squared.
And then you divide the top layer by the bottom layer.
Right. You divide the top by the bottom. Pounds divided by pounds completely vanishes. Inches cubed divided by inches squared leaves exactly one single inch.
It leaves exactly inches. The force variables, the weight variables, the area variables, they all interact, fight each other, and cancel each other out until the only dimension left standing is the physical length you were trying to find in the first place.
For anyone designing anything, this is your ultimate failsafe. If you invent a brilliant, revolutionary new formula to calculate how far a beam bends, and you run the dimensional analysis, and the left side of your equal sign is inches, but the right side cancels out to degrees Fahrenheit, you are wrong.
You were absolutely wrong.
It doesn't matter how pretty the math is. Your physical model is flawed. The units never lie. Dimensional analysis forces your math to keep its grip on physical reality.
It forces the mathematician to remain honest to the physical universe. You just can't cheat the dimensions.
We have covered a massive amount of ground today. We translated the language of limits. We visualized bending moments with smiles and frowns. We uncovered the invisible enemies of creeping heat and corrosive rust. And we proved our math with dimensional analysis. As we wrap up this deep dive into Roarks, what is the final thought you want to leave the listener with?
I want you to consider a thought experiment based on the invisible forces we just discussed. Creep, corrosion, fatigue, and changing temperatures. Look around at the aging infrastructure in your own city. The bridges you drive over, the dams, the towering skyscrapers. A vast majority of those structures were engineered 50 to 100 years ago.
Oh, yeah.
The engineers who built them used Roark's formulas, and they did the math correctly based on the expected weather, the expected traffic, and the expected high temperatures of that era.
Right. They calculated their allowable stress and their safety margins based on the environment they lived in a century ago.
But what happens when the global environment drastically shifts?
Yeah.
If a steel bridge is now experiencing summer heat waves that last longer and burn significantly hotter than anything the original engineers modeled for, we are radically increasing the rate of creep.
Wow.
We are accelerating the corrosive environment with wilder storms. We have to ask ourselves, are we entering an era where the foundational math of our physical world, the safety margins baked into every concrete pillar and steel beam we interact with, requires a massive recalculation?
That is a staggering thought. The math in the book didn't change, but the physical reality it was mapping did. The boundary conditions of our entire planet are shifting, and the math is going to have to catch up. Remember, design junkies master the critical few, or the trivial many will master you. If you're leaving this episode with something you didn't arrive with, drop a comment. Takes you a few seconds, but it tells me this workbench is worth keeping open.